Welcome to Lecture 1.4, Inner Products and Orthogonality. Thus far, in this class, we've introduced the notion of a vector space and related concepts. Now, a vector space consists of a set of vectors that is closed under addition and subtraction and scalar multiplication. What we have not done yet is talk about how to measure the lengths of vectors or how to measure the angles between them. Now, this is something that we know how to do in Rn. It's just basic Euclidean geometry. But we would like to do the same thing in more general vector spaces. For example, spaces of functions or polynomials, infinite dimensional spaces. It's not clear how to do this. So in this section, we will revisit Euclidean geometry and see really what's behind the scenes of measuring lengths and angles. And the answer is a dot product. That is a concept that we can extend to general vector spaces, and we call that extension an inner product. When we define an inner product in a general vector space, we get a notion of what it means for vectors to be perpendicular, and we call that orthogonality. So that's the second part of this title. So then we will look back at all the mileage that we get just by defining a dot product in Euclidean geometry and see how much of that carries over to the general case of vector spaces of functions. Let's begin back in Rn and remind ourselves what the dot product is. So the dot product of two vectors v and w, if we write them as n tuples of numbers, say a1 up to an and b1 up to bn, well, that's just v dot w, which is the sum from I equals 1 to n of ai times bi. So we just multiply these two vectors component by component and add that up. Let's recall how this is all related to the definition of the length or the norm of a vector v, which we denote with this double absolute value sign. We say norm v, and geometrically that is just the Euclidean distance from the vector v to the origin 0. Now, Pythagorean's theorem gives us a formula for this distance. The norm of v is the square root of v dot v, which is the square root of a1 squared plus a2 squared all the way up to an squared. This helps us connect the notion of a dot product with the notion of norm, but it doesn't really help us understand what v dot w means geometrically. So to do that, we'll pick a special v and w, and then we'll argue why there's nothing so special about this choice after all. First of all, we'll pick v, an n-dimensional space, to lie on the x-axis, or if we prefer, we can call this the x1 axis. So it's some scalar times e1, and recall that e1 is just the vector of all zeros except a 1 in the first coordinate. Next, we'll pick w to be in the xy plane, or maybe the x1, x2 plane if you prefer. In other words, w is going to be a linear combination of v1 and v2. So let's draw a picture of this. So here's the, let's call it the x1 axis and the x2 axis. So let's pick v to be on the x1 axis. So v is just a scalar multiple of e1. And then w is a linear combination of e1 and e2. So it's something like this. So now let's try to describe these vectors in coordinates. So x1, or I should say v, let's write it over here. So v, the x1 coordinate of that is just the norm of v, because everything is in that direction, and then it's 0 in every other direction. So it's 0 in the x2 direction, and 0 all the way in the xn direction. And then what's w? So let's do some trig to find out what w is. So in the x1 direction, w is, what's that? That's just the norm of w times the cosine of this angle theta. And in the other direction, this is the norm w times the sine of theta. So in other words, w is, in the x1 direction, it's norm w cosine of theta, In the x2 direction, it's norm W sine of theta, and then in every other coordinate, it's 0. Okay, so given this, what is v dot w? Let's write that out. So v dot w, if we multiply coordinate by coordinate, well, we get that product, and then we get 0 times w sine, and every other entry is 0. So v dot w is norm v times norm w times the cosine of the angle between them. So this is a geometric picture, or geometric meaning of what the dot product between two vectors is. So to summarize, by basic trigonometry, we write v as an n-tuple of these numbers, and w as an n-tuple of these numbers, and we'll call this a proposition. The dot product of any two vectors v and w in Rn satisfies the following relation. V dot w equals norm v times norm w times cosine of theta, where cosine is the angle between them. Equivalently, we can solve for cosine of theta and describe the angle theta purely in terms of a dot product. So cosine of theta is v dot w divided by norm v times norm w. Now we can actually define the angle in this manner, although technically, as you know, there's multiple values in 0 to 2 pi that give you the same angle. So it's probably better to define the cosine of the angle like this. Now I should clarify something that I said. I started with, above, a very special v and w. V was on the x-axis and w was in the xy plane. And then I jumped to say that this dot product formula holds for all vectors. But that shouldn't be too much of a stretch. If you think about it, if we have two vectors v and w in n-dimensional space, we can always rotate and translate, not even translate, just rotate them until v is on the x-axis, or the x1 axis, and w is in the xy plane. And this rotation doesn't actually change the angle or the dot product at all. So it's not hard to see that our special v and w wasn't so special at all. In other words, this formula holds for all vectors in n-dimensional space, regardless as to whether they are on any axis or in the span of E1 or E2. To summarize, what we did on the last slide is we took the notion of a dot product, and that alone gave us a definition of length and a definition of angles. And in fact, even more is true. This gives us a whole notion of geometry. Basic Euclidean geometry simply follows from the dot product. I know that sounds remarkable, but let me show you that right now. So let's take v and w, any two vectors, and let's take v plus w and dot it with itself. And if we do that, we get v dot v plus 2v dot w plus w dot w. So the distributive law here holds. And the left-hand side of this, as we know, any vector dot itself is equal to the norm of that vector squared. So this is all basic. Nothing here should be new. But now, let's take v minus w and take the dot product of that with itself. And how is that going to change? It's going to be the same thing as above, except this plus is going to be a minus. So we have v dot v minus 2v dot w plus w dot w, and well, this left-hand side we know is equal to the square of the norm of v minus w. I've written this in blue here because I want to show you that this is essentially the law of cosines. So v dot v is the norm of v squared. W dot w is the norm of w squared. And what we just saw in the previous slide, that last proposition, v dot w is the norm of v times the norm of w times the cosine of the angle between them. To summarize, this last equation above in blue, instead of handwriting it, here it is typed. That's just the law of cosines. So not only do we get a notion of lengths and angles from a dot product, but we get the law of cosines. But it doesn't just stop here. Let's take any unit vector, let's call it n, in n-dimensional space. And by unit vector, I mean that the norm of n is equal to 1. Then the projection of a vector v onto this unit vector, we'll write it like this, proj sub n of v, is just v dot n. This is something that you likely remember from vector calculus. If not, we'll do an example. Consider the vector 4, 3, which is 4e1 plus 3e2 in R2. Let me draw a picture of this. So here's the vector 4, 3. Remember, it doesn't matter if we write it vertically, like this, or an ordered pair, like that. But let's project this vector onto e1 and e2. So e1, of course, is 1, 0, and e2 is 0, 1. Now it should be clear geometrically that if you project v onto e1, you get 4. So that's the length of v in the e1 direction. That's how you should think of a projection. And if you project v onto e2, you get 3. So that's the length of v in the e2 direction. Now algebraically, v dot e1 is 4, 3 dot 1, 0, which is 4. You just pick off that 4. And v dot e2 is 4, 3 dot 0, 1, which is 3. Here is that same calculation written as ordered pairs instead of vertically. The big idea here is by defining the dot product in Rn, we get for free a notion of Euclidean geometry. That is, we get natural definitions of concepts such as length, angles, and projection. To do this in other vector spaces, we need a generalized notion of dot product. Think about what this might mean. What is the dot product in a vector space of polynomials, or a space of smooth functions, or the space of 2 pi periodic piecewise functions? We want to define an inner product in a vector space to have the same fundamental properties of a dot product. Before I give you the formal definition, I want to show you the notation that I'm going to use. So in Rn we write v dot w, and in a general vector space I'm going to write angle bracket v comma w, like this. Now I'm still going to call this v dot w, because that's so much easier to say than angle brackets or something, or just the inner product of v and w. It's one syllable, and it should always be clear from the context what I'm talking about. If I'm talking about a space of functions, then I'm clearly not using the standard dot product in Rn. So our definition, you can think of it as a generalization of a dot product. In other words, we're going to define an inner product up here, and the standard dot product is a special case. It is an inner product. So let's let V be an R vector space, a real vector space. We will later define a similar notion in a complex vector space. It's almost the same, but for right now, let's just focus on real vector spaces. So a function, so I'm going to use this angle bracket, and I'm going to put these 2 dashes in here to denote the fact that V and W are missing. So this is a function where there's 2 entries. So that means that these 2 entries both come from V, so it is a function from V cross V. So it takes in ordered pairs of vectors and spits out a real number. So a function like this is a real inner product if it satisfies for all vectors u, v, and w, and for all scalars c, the following conditions. First of all, u plus v dot w must equal u dot v plus v dot w. CV times W equals C times V dot W. V dot W equals W dot V. And finally, V dot V is always non-negative, and equality holds if and only if V is the zero vector. The first two conditions above are called together bilinearity. The third is called symmetry, and the fourth is called positivity. It should be fairly self-explanatory why these last two got their names, so I'll say a few words about bilinearity, in particular how it differs from linearity. So recall that a linear map, F, is a map from V to the field, let's say R, because we're looking at an R vector space here, and it satisfies the property that F of A x plus by equals A f of x plus B f of y. So a bilinear map above, I'll use G for a bilinear map. This is a map from V cross V to R. So it's fundamentally different because it takes two inputs, so it doesn't just take a single input V right here, it takes two inputs. So I could write something like G of AX plus BY in the first coordinate and CX plus DY in the second coordinate. And I want to ask, what does something like this equal? Well, bilinearity means that if you fix one of the coordinates and treat it as a constant, then it's linear in the other coordinate. So to answer this question, that means if I take G of AX plus BY, and let me just fix this second coordinate, instead of whatever this is, I'll just write it as a line, then that equals A times G x comma blank plus B times G y comma blank. In other words, if you fix this second coordinate, then you can break apart sums and pull out constants. So if you look up here in the definition above, here if you fix this second coordinate W, so just pretend that's not there, notice that you have linearity because U plus V is a U here and a V here. And again, if you fix this second coordinate, pretend it's not there, then this C you can pull out right there. One last comment. Here I said V is an R vector space. So this is vector spaces where the field are real numbers. The definition is slightly different for complex vector spaces. So in particular, this third condition of symmetry, it changes slightly. You have to put, if you swap the order of V and W, you actually have to put a bar, a complex conjugate over this. And the other difference is this, in this second one, so you can pull out a C from the first coordinate, but if you want to pull out a C from the second coordinate, oops, let me make that an angle bracket, you have to put a complex, you have to conjugate that as well. So if you want to pull out this C from here, you have to put a bar on here. So we won't mention this much in this lecture. I think I'll do an example with a complex vector space though, but later in the class when we study Fourier series, we'll have an entire lecture devoted to complex inner product spaces. So here's a remark that should not be a surprise. I've told you it was coming, but defining an inner product on a vector space gives rise to a geometry. Right away we get a notion of length, of angle, and projections. In particular, the length of a vector we can just declare to be the square root of V dot V. The angle between vectors V and W, we can say that that's cosine, where the cosine of the angle is V dot W divided by norm V times norm W, where norm V and W we just defined above. And again, we have to be careful because there are two values of theta in 0 to 2 pi that give the same cosine, but that's elementary. That's something that we can deal with. Finally, we have a notion of projection. If n is a normal vector or a unit vector, meaning it has norm 1, using this definition of norm defined above, then we can project any vector v onto n by defining the following. And here I've split it up into two parts. So lowercase proj, projection of v onto n, I'm going to say is just the dot product of v and n. So it's the inner product, v dot n. So that is a scalar, that is a number. Sometimes we want to speak of the actual unit vector in the direction of n, whose length or norm is this dot product. So then I'm going to write that as capital proj, capital projection of v onto n, and that's just the same quantity multiplied by the unit vector n. I really don't know if this is standard, this lowercase and uppercase. I get the sense that a lot of people and books are sloppy. Sometimes when they say projection, they mean the scalar. Sometimes they mean the vector of that norm. So I'm going to put my foot down and be consistent. And henceforth, when I use a lowercase p, I mean the scalar, and uppercase p, I mean the vector. And this, or at least the lowercase one, is the length or the magnitude of the vector v in the n direction. Now we come to the concept of orthogonality. Two vectors, v and w, in our space are said to be orthogonal if their inner product is equal to 0. A set v1 up to vn of vectors is orthonormal if take any two of them, take their inner product, you get 0, so they're pairwise orthogonal, and all of them have unit length. So orthonormal, think of it as meaning orthogonal and they're all normal vectors. Here's how you should think about this. Orthogonal is the abstract version of perpendicular. So just how a dot product is a special case of an inner product in Rn, perpendicular is a special case of orthogonal in Rn with respect to that dot product. So in Rn, two vectors, v and w, are perpendicular if and only if their dot product, v dot w, is 0. So that's what we want to capture by the notion of orthogonality. In a generalized inner product, or generalized dot product, which is an inner product, we say that v and w are orthogonal if and only if v dot w is 0. Next, orthonormal means perpendicular and unit length. An equivalent definition of this one above, if you wrap your head around it, this just says that they are pairwise perpendicular or orthogonal and each have unit length, is the following very concise definition. If you take the inner product of any vi with any vj, well, you get 0 if I and j are different, and you get 1 if I and j are the same. Notice that this part where vi.vi is 1, that's equivalent to vi having norm 1. And since this is a key idea, I really want to emphasize that orthonormal bases are really, really desirable. So later we're going to look at more abstract vector spaces of functions, and if we can somehow come up with an orthonormal basis, our life is much, much easier. Let's do some examples. Start with Rn. I've already said this before. The standard dot product, which is just v dot w, and this is how we define it, is an inner product. The set E1 up to En that you know and love is an orthonormal basis of Rn. These are mutually perpendicular and they all have unit length. This means that we can write each vector in Rn, say v, uniquely in this orthonormal basis. So v is just a1 up to an, and those coefficients are just the coefficients of the corresponding ei. And so in other words, ai is just the projection of v onto ei, or v dot ei. And here I'm using lowercase p. So let me do an example of that. Let's do that same example we did before, where this is v equals 4, 3. So here is E1 and here is E2. So all this is saying is that 4, 3 can be written as 4 times E1, or 1, 0, plus 3 times 0, 1, or E2. And moreover, this 4, all that is that is the projection of V onto E1. In other words, it's 4, 3.10. And this 3, that is just the projection of V onto E2. In other words, 4, 3.01. So that's why we often use this n-tuple notation. We might write this as 4 comma 3, which again is the same as writing it vertically, 4 and 3. This works in any number of dimensions, not just R2 or R3, and in fact it works not just for E1 up to En, this particular orthonormal basis. We can do the same thing in a different orthonormal basis. For example, if we had instead, I don't know why you'd want to do this, but, well, actually I do know why you might want to do it in some cases. Suppose we had chosen, let me call this E1 prime and E2 prime. This orthonormal basis, say these are 45-degree angles, well, obviously this here is 90, and we could have done the same thing. We could have written 4, 3 in this orthonormal basis using this projection trick, and it works out just like we did above. Obviously, we're going to get different coefficients. Our second example, let's let V be the space of 2 pi periodic functions, and here I'm going to say complex valued functions. So the inner product, as I said above, has to be a little bit different. We have to worry about complex conjugation, and I won't deal with that now. I'll just tell you what the inner product is. We can define an inner product as follows. This is not the only inner product, but this is a very nice inner product. So we say that f dot g is 1 over 2 pi times the integral from negative pi to pi of f of x times the complex conjugate of g of x dx. Now, why would you want to do that? Well, one way to sort of motivate it is if you think about what v dot w is, that's the sum from I equals 1 up to n of vi times wi. So you add up these guys coordinate by you multiply them coordinate by coordinate and add that up. Well, here you have a continuous or piecewise continuous function on a whole interval from negative pi to pi. So this might be f, this might be g. So what's the analog of multiplying these things together pointwise and adding that up? Well, that's what this is. It's f times g integrated from negative pi to pi. Now there's a few details that we will discuss later, but not now. Namely this 2 pi, and especially this complex conjugation symbol. But think of this really as the continuous version of the classic dot product in n dimensions. So why do we define it this way? Why the 2 pi? Well, this inner product is actually really, really nice because the following set, this infinite set of complex exponentials e to the inx, where n is any integer. In other words, this set here is in fact an orthonormal basis with respect to this inner product. So why is that? That's not a magical statement to say. We can verify that. Let's check. So let's check that. Take the inner product of any two of these guys. And what do we have to do? We have to check that that is 0 if n and m are different, and 1 otherwise. So let's take e to the inx and take the inner product of that with e to the imx. Now this, by definition, is 1 over 2 pi times the inner product of, times the integral, from negative pi to pi of e to the inx times e to the minus imx dx. Okay, hold up. Now why did I make this negative. So remember that what we need to put here is the complex conjugate of e to the I mx. And if you recall basic complex numbers, on the unit circle, any point on the unit circle, angle theta is e to the I theta. And the complex conjugate of that is what you get when you reflect that across the real axis. You make the imaginary part negative. And that, of course, is just e to the negative I theta, because the angle here is negative theta. So this integral, let's just do it. It's 1 over 2 pi times negative pi to pi of e to the, well, what is this? I times n minus m times x dx, right? We can do this integral. This is 1 over 2 pi times 1 over I times n minus m times e to the I n minus m x from negative pi to pi. So what do we have here? This thing here is an integer. So let's call this, let me just call that k to make things easier. So this is this whole constant, I'm not going to rewrite it, times e to the, how do I want to write this? I k pi minus e to the minus I k pi. And it's easy to check that e to the I times any integer times pi is negative 1 to the k. Now why is that? Because if you look at the unit circle and you go around some integer number of times, so if you go around once, e to the minus I pi, you're here. Twice, e to the 2 pi I, e to the 3 pi I, e to the 4 pi I. So you just get either positive 1 or negative 1, depending on whether k is positive or negative. Well, k and negative k have the same parity, so both of these things, both this and that, are negative 1 to the k, so this equals 0. And here, of course, I'm assuming that n and m are different. So we have just verified that any two of these functions are indeed orthogonal. They are, think of it as perpendicular with respect to this clever little, with respect to the geometry that results from this clever little inner product. Let's check that each of these has norm 1. So let's take e to the I n x dot e to the e to the positive I n x. I'm a step ahead of myself. Well, this, by definition, is 1 over 2 pi times the integral from negative pi to pi of e to the I n x times e to the minus I n x. There's the negative sign, because we take the complex conjugate of this. And now the product of these things is just 1. So this is 1 over 2 pi times integral from negative pi to pi of dx. And that, of course, is just equal to 1. So yes, each of these functions is also unit norm or unit length with respect to this inner product. So indeed, it was pretty easy to check that this collection of functions is orthonormal. Now, what's not obvious is that it's actually a basis. In other words, that this actually spans this set of functions. And that's something, there's a lot of details, we will go into it later, and there are a few minor details that we are sweeping under the rug because this is an infinite dimensional vector space. But I promise you, we will come back to those and clear those up. But for right now, for all intents and purposes, you can think that, yes, this is an orthonormal basis of this vector space of 2 pi periodic complex functions with respect to this incredible inner product. That means, because this is the basis, we can write each function, each 2 pi periodic complex valued function, I've omitted c for clarity, uniquely comes from the fact that it's a basis, as the following. F of x is some linear combination of these basis vectors. There's infinitely many of them, so we have to sum from negative infinity up to infinity. Now, not everybody likes this double sum business. So what you can do is you could just take the n equals 0 term here and pull it out. That's a constant. And then package the positive n and negative n terms together and write this as a normal sum from 1 to infinity. So some people prefer this because it's nice and concise, and others prefer this because it only goes in one direction. Either way, not only do we have the fact that such a function can be written very nicely like this uniquely, but we amazingly have a formula for the coefficients. We know how to do this as well. That Cn is just a projection of the function f onto that corresponding basis vector. Now what's the projection? Remember, it's with respect to this inner product. It's just the inner product of f with that basis vector, that unit vector. And what is that? Well, that's just 1 over 2 pi times negative pi to pi f of x times e to the minus inx dx. Remember, the minus sign is here because we take the complex conjugate of this. So that really is a remarkable fact. We've done nothing but define a vector space abstractly, and then define a notion of this inner product that behaves just like a dot product, and all of a sudden we get a formula for how to decompose any 2 pi periodic function into these fundamental frequencies, these complex exponentials. And here's a formula right here involving an integral of how to do that. Here's our third and final example, and it's very similar to the previous example. But now let's let V be the space of 2 pi periodic real valued functions. Here we define an inner product as, well, f dot g is 1 over pi times negative pi to pi of f of x times g of x dx. And here, because we have a real vector space, we don't have to worry about putting a complex conjugate on that second argument like we did before. Now that's nice because we don't have to deal with complex numbers, but this is probably not quite as elegant as the previous example, because now the following set is an orthonormal basis with respect to this inner product. So the only weird thing here is this constant term, and it's because you get all of the cosines and you get all of the sines, but when n equals 0, well, sine of 0 is 0, so there isn't a sine term for n equals 0, and cosine of 0 is 1. So you might think that the constant function 1 should have unit length, or norm, but in fact it doesn't, and we can check that. So the norm of the function 1 is, well, the norm squared is the inner product of 1 with itself, which by this definition is the integral from negative 1 over pi times the integral from negative pi to pi of 1 dx. And if you compute this, you get 1 over pi times 2 pi equals 2. So in fact, the norm of the function 1 is equal to the square root of 2. So a little bit weird here, but it's because we're doubling up really on this n equals 0 term. Now, I'm not going to verify that this is an orthonormal set like I did before, but I would say, I'll tell you what this means, or how you would verify it, is you verify that if you take cosine of nx dot sine of nx, so if you do, or let's say mx, because they might be different, that is 1 over pi times negative pi to pi cosine of nx sine of nx dx. That's not a fun integral to do, but there's a few trigonometries you can apply, and you will get 0. And similarly, if you do cosine of nx, and let me do cosine of mx here, you'll get a similar integral. Negative pi to pi, you get cosine of nx cosine of mx dx. Now here you got to be careful because you're going to get 1 if n and m are equal, and 0 if n and m are different. And then similarly, you have to check that the same thing holds with sine of nx and sine of mx. So it's a little bit more complicated here. It's not quite as easy because you have sines and cosines. So that's why it's not quite as elegant in this form as the complexity inner product, which is why I showed you that one first. But in some ways, this is actually nicer because we know what cosines and sines look like. So these things are really the fundamental frequencies. You think of them as sound waves. So this is sine of x, sine of 2x looks like that, sine of 3x looks like that. And so this really means that any real valued 2 pi periodic function, well, let me actually erase this and show this to you. Every real valued 2 pi periodic function, I've omitted the r there because I've already set it up here, can be written uniquely as a sum linear combination of these sine and cosine waves, and possibly scaled by a constant. So we can write it like this, and we actually have a formula for these ANs and these BNs. Now forget this n equals 0 term just for a moment. I know it's weird, like where did that 2 come from? Well, AN, for at least n equals 1 to infinity, is just the projection of f onto this cosine wave, which is, well, f dot cosine nx. And we have a formula for that using our inner product. That's just 1 over pi times the integral from negative pi to pi of f of x times cosine nx dx. And similarly, this bn term, we have a formula for that. Bn is the projection of f onto sine of nx, that unit basis vector, which is just the inner product or the dot product of, well, I guess inner product of f with sine of nx, and that is just an integral, 1 over pi times the integral from negative pi to pi of f of x sine of nx dx. So that's remarkable. Now, one comment about this term, why is that? What is that 2 doing here? Yes, it is related to this root 2, essentially because of this special case here. Technically, we would say that the coefficient of this would be the inner product of f with 1 over root 2, and if you do that, you actually get a slightly different formula than this one right here. So the reason why you put a 2 here is, for the short answer, is because it makes the formula for a naught be exactly the same as the formula for this. So it turns out that a naught is 1 over pi times negative pi to pi times f of x. What's cosine of 0x? That's just 1. So f of x dx. So we put the 2 here because it makes this formula work out exactly like the formula for an. Just plug in n equals 0. Okay, so more on this later. I want to conclude with an important remark. Sometimes we have at our disposal an orthogonal basis that's not necessarily orthonormal. So we have v1 up to vn, and sometimes it's quite a hassle to make it orthonormal. Or I guess not really a hassle, it just makes it really messy. And it's a lot more convenient to just have an orthogonal basis. In this case, there's still a simple way to decompose an arbitrary vector into this basis. And it all stems from the basic observation that if you normalize each of these vectors, then what you get is an orthonormal basis. For example, if you have this set which is not unit length, and you normalize each one of them, maybe you get, so this is v1, this is v1 normalized. Well, that doesn't change the angles, that just changes the lengths, scales them down to 1. So if this is an orthonormal basis, that means that you can write your original vector v, you can decompose it into this orthonormal basis by projections. So ai is just v dot vi normalized. Now we can pull out this constant 1 over the norm of v out in front, and now we just get v dot vi divided by norm vi. And we have a formula for the norm of VI, that's just the square root of VI.VI. So what I'm going to do now is I'm going to just rewrite what we have here on the left. I'm just going to regroup things. So I'm going to pull that out, and I'm going to put those things together and write this as V1 times the scalar A divided by norm V1, all the way up to Vn times the scalar An divided by norm Vn. Here's what that looks like typed. So the scalars are now in red. And I'm going to rename these scalars. So each AI divided by norm VI, let me just call that CI. So this one is C1 and this one is Cn. If I do that, then I have C1V1 plus ... to CnVn. And I have a formula for the CIs. C1 is just A1 over norm V1 and so forth. So CI is just AI divided by norm VI. And this is what we wanted. Remember, we started with an orthogonal basis, and we said, given an arbitrary vector, let's decompose that into that basis. In other words, write it as a linear combination of the basis vectors and come up with a formula for the CIs. And here's that formula. Now AI is right up here, and VI, norm VI, recall what that is. That's just the square root of VI dot VI. So that's the square root of VI dot VI. So what happens if we tack on an extra root of this down here? Well, then the square root goes away. So we just get V dot VI over VI dot VI. So there is our formula for the CIs. If you prefer, you can write that as V dot VI over norm VI squared. So this is a nice formula to remember if you want to decompose a vector into a basis that happens to be orthogonal, just not necessarily orthonormal. Notice that if this is in fact orthonormal, then this term in the bottom here, Vi dot Vi, just becomes 1, and we get our simplified formula V dot Vi that we had before.